What's up, trigonometry? This is Mr. Carlson, and what we are going to be doing today is just 5.6 graphs of tangents and also other trig functions. So that includes cosecant, secant, and cotangent. We're going to go through the bell work. We're going to go through the objective, essential question, 5.6, and then closure and homework. So these are the only two bell work questions I have for you. I know they're just review, so you don't have a homework quiz today, but they're just review for your tests next week. Let's just say that, okay? So what do? I want to determine the amplitude, period, and then phase shift, and we're going to go to Desmos to graph it really quick. So what's the amplitude? My amplitude is 1. Excuse me. My period, what's my period? Well, my period is 2 pi all over b. So I'm going to cloud that. And so that equals 2 pi. And then all over b, my b is actually 1 as well. It's right here. So that's 1. So that means my period is 2 pi. And then my phase shift, what's my phase shift? This is c all over b. My c, it's pi all over 4 because it has a built-in negative. So pi all over 4. And then built-in negative. So that's positive. And then all over 1. So this is just pi all over 4. Awesome. So that's my phase shift. And then I'm just going to go to Desmos to see what it looks like. I realize that on Math Excel, some of you do need to actually type it in. Some of you do need to actually graph it, I guess. But I'm not going to be doing that by hand right here. For the sake of time, I'm just going to plug it in. So sine, and then x minus pi all over 4. Okay? Sine x minus pi all over 4. So we're going to go here, and we're going to just do sine x minus pi all over 4. So I'm going to change this. This was 1. My b was also 1. And then my c was pi all over 4. This is what it looks like. Okay? This is what it looks like. And depending on your Math Excel, like what it wants, like the restrictions or whatever, you can also restrict this. If I wanted to restrict this, I can do fancy braces. Let's just do from negative 3 pi all over 2, and then x, and then let's just go from to 2 pi. Let's just do that. So I can restrict it here and just make it look like that if I wanted to. That's how you do restrictions. So if you don't know how to do restrictions on Desmos, boom, there it is. Okay, that's how you do restrictions. And then I can kind of see like what I want in this graph, what are the actual points here and so forth. Pretty cool. Pretty cool. That's the first one. Let's go back. Cosine. So cosine, my amplitude is 1/2. My period is 2 pi all over b. So 2 pi all over 4 in this case, which reduces down to pi all over 2. So it has a length of pi over 2. And then my phase shift. My phase shift, what's my phase shift? It's c all over b, which is c is just 2 pi. Remember, built-in negative, don't take the negative with it. If it was positive, you would take the negative with it. And then all over b, which is 4. So my phase shift, my starting point is pi all over 2. Okay, so let's go back. This is 1/2 cosine 4 and then 2 pi. So 1/2 cosine and then 4, yep. My c value is 2 pi with no d. Perfect. Okay, so this is what I have. This is for sine, so don't want to do that. Let's do cosine. Let's actually just paste that right in there. Okay, so this is what it looks like for cosine. This is what the cosine graph looks like. And now it's starting out in pi over 2, so maybe let's reduce this down to pi over 2 to 2 pi. So this is what the true cosine would look like. And if I just want one section of it, I would just do, that's the actual length of it. Okay, just 1/2 pi, or pi over 2. That's the length of it. Okay, pretty cool. Play around with this. Okay, please play around with it. Mine looks a little bit different. I kind of upgraded it a little bit so than yours, but just play around with it. Of course, it's gonna getting some used to, and that's okay. Like, please get used to using Desmos, using the trig graphs and everything, because they really, really do help. It really does help. All right. Awesome. So that's what it looks like. I'm going to erase and we're going to get started. How do I graph the tangent, and how do I graph the reciprocal functions? Specifically, though, we're going to be looking at how it relates to the unit circle. That's a question that I'm going to probably leave up to you. It does relate to the unit circle, obviously, but I'm going to leave it up to you. We're just going to learn the tangent, cotangent, cosecant, secant graphs in that order. All right. So what I want you guys to do is actually, yes, practice using Desmos. Okay, you don't need to type theta for the variable theta or pi or anything, but pi for pi. If you go to this function, it's already on Google Classroom. You should have already pulled it out. Okay, go ahead and just pull this up, and then basically kind of play around with it. By play around with it, try to type in these functions. Now, you can get a brand new Desmos tab if you want and just start typing in theta if you would like. You don't need to do that. You can do x if you want. In this graph, I have for x's and not thetas. So don't be typing x if it's a theta. So in this, just don't type theta, type x. Okay? But try to play around with it, see what happens. So plug in the normal tangent graph. Do the normal tangent graph. What do you notice? Do a cotangent graph that's a little bit more complicated with these restrictions. And then what do you notice with that? Same thing here, cosecant graph with these some transformations, and then of course the secant graph. These are some funky looking graphs, and I just want to just literally give you a second to go ahead and do these. And just what do you notice about them? Okay, I'm not going to plug them in myself. I already know what they look like. Okay, but what do you notice about them? And I really do encourage you to actually do this, to try to explore and see what these graphs look like, so that when I start going through it, you're not as afraid and not as okay. So go ahead and pause the video, and then we'll get started. All right, graph of a tangent function. I'm going to show you what the tangent function looks like. Okay, not on this screen, but on just my general basic just screen right here. What does the actual tangent function look like? It looks like this. Okay, this is your tangent function. I'm actually going to change this to pi over 2. This is what your tangent function looks like. Really funky. Okay, really funky indeed. Of course, does it go on forever? Yeah, I have it restricted. Okay, so I restricted it a lot, and I built that so that it can be restricted. So yeah, I've done all that. Don't mess with this. Okay, don't mess with it. It's restricted, and then you also have what we call asymptotes here. So this is what the real graph looks like, and then what I added was asymptotes. Okay, so asymptotes basically you're going to have with tangent. Why do you have asymptotes with tangent? Well, you're going to have undefined values at tangents. That's why. Okay, you're going to have undefined values, specifically every pi units. So right here, or every pi over 2 units. So right here, you have this function. It's pi over 2. You have it basically not existing there. Okay, the tangent gets really, really close and really, really close, but it never actually gets to equal that. Okay, and that's the cool thing about the tangent graph. And same thing with 3 pi over 2, same thing with 5 pi over 2, and so forth, negative pi over 2. So the tangent graph, you start to see what happens here. What happens is it's undefined at certain areas. Okay, it's undefined at certain areas, and that's what we have to kind of look at. Now, if I actually do a negative, if I put a negative here, it actually gets flipped. which is pretty crazy. The whole thing gets flipped and everything. So we're going to be looking at the tangent graph as of right now, and then we're going to go to the other three. But I only have one example for each. That's not because they're really hard. It's just because they take a while. That's all. But we have Desmos, and it's going to be a lot easier. So these are the characteristics. These are awesome characteristics. So the domain is all real numbers except for odd multiples of pi over 2, and we've already said that. It repeats pi over 2 units. It has an undefined value. Okay, the range is all real numbers. Your period is pi. So the reason why it's a period of pi is because, again, it is undefined. Okay, it's undefined. If I actually go back, it's undefined. So right here, your period, your length from here to here, okay, that's pi units. Okay, so your period is pi, but it has an asymptote at every odd multiple, 1 pi over 2, 3 pi over 2, 5 pi over 2, every odd multiple of pi over 2, okay? All right. It is an odd function, okay? It doesn't have a real nice symmetry there, and we already know it's an odd function from a couple days ago. And then the points on the graph. This is really interesting right here. The points on the graph is 1/4 and 3/4 of the way between consecutive asymptotes. So when we graph it, I'm actually going to, and when we graph cotangent, I'm going to show you what that means. It actually is very helpful when we graph. Also, what's very helpful is this. So I would definitely make sure you get those two down, because these are basically tell us how to graph it. An x-intercept occurs midway between each pair of consecutive asymptotes. So we look right here, each way in the middle of these little branches, we have the asymptotes. Those are the asymptotes, but this is the branch. And in the middle of that branch, in the middle of this tangent graph, we have straight up an x-intercept. So in the middle, we have straight up an x-intercept. In the middle, we have straight up an x-intercept, and so forth. And that does not change. Even if I change the tangent graph, I can change it to whatever I want. That does not change. Okay? So like I said, this is what it looks like. That's really nice. I already had it on the other screen, so you don't need to really write that down. But what we're going to be asking is, why does tangent look different than sine and cosine? The reason, again, I want to reiterate this. I've already said it to you multiple times. The reason why it looks different is because it actually has undefined values. Okay, cosine and sine do not have undefined values anywhere on the unit circle, but tangent does. Okay, if you take 1 divided by 0, it's undefined, and that's literally tangent of pi over 2. It's undefined. It's 1 divided by 0, sine over cosine, y all over x. Okay, so here are the steps of how to graph a tangent function. First of all, you need to find its asymptotes. Okay, how do you find its asymptotes? It's actually very simple, but I'll show you. You need to find its asymptotes. Second of all, you need to plot the x-intercept midway between the asymptotes. We already got that from the last slide. And then find the 1/4 and 3 points. Okay. This is the helpful formula for us in order to find the asymptotes, so make sure you write that down. And then this right here, graph the tangent. We're going to graph this. Now, I'm going to do this one by hand, but I'm also going to show you how to do it on Desmos. Tangent graphs and cotangent graphs are actually very, very easy to do by hand. I mean, extremely easy to do by hand. So I'm going to show you how to do it. I think it's a little bit easier how to do it by hand than sine and cosine, to be honest. But all right, what do I have? I have this formula. This is the formula I use. So this is always going to be negative pi all over 2. And this is always going to be pi over 2. Now, what's the b minus c part? The b minus c part is really just this middle part. Now, you can't really see it with this graph, this function I'm looking at. I can't really see it. So I'm actually going to expand it and say that this is 2 times tangent in parentheses 1/2 times x minus 0. Okay, this right here, this is really your bx minus c part. Okay, that's your bx minus c part. So what I'm going to do is take that and implant it right here. That's what I'm going to do. So this is 1/2 x, and then of course minus 0. But do we really need to write the minus 0? No, not really. So what do I do here? Well, what I do is just basically multiply everything by 1/2. I mean, by the reciprocal, which is 2. So I can multiply this whole thing by 2, multiply that by 2, multiply by that by 2, and then every 2 goes poofy. So then what do I have? Negative pi is greater than x, but also at the same time less than pi. So what does that mean? Okay, what does that mean? This means that those are where our asymptotes lie. Those are where our asymptotes lie. Now notice, I'm not trying to find the period at all. You notice that? I haven't been trying to find the period because there's no period that really exists on tangent except for pi. I mean, that's really the only period that exists. And so basically, our asymptotes lie right here, okay, at negative pi, and then right here at pi. Come on, at pi. So those are where my asymptotes lie. Now what I want to find the 3 midway points, or sorry, the intercepts. I want to find the intercepts of midway between the asymptotes. So between the asymptotes, the midway point is right here. And I'm actually not, the midway point will be here, and then the midway point would be here. Okay? What is this going to look like? It's going to look something like this. It's going to go up like that. It's going to go like up like this. Okay? But before I do that, I want to use the amplitude to plot the 1/4 and 3 waypoints. What's my amplitude? My amplitude is 2. Okay, so if this is 1, that means this is 2. This is -1. This is -2. So then I'm going to use my amplitude. I'm going to plot the 1/4 and the 3/4 points. So the 1/4 point, when just basically chunking this, okay, this right here gives 1/4. That's 1/2 total. This is another 4th, and then this is another 4th. So each block, each like 2 blocks right here on my grid equals 1/4. So this right here is 1/4. That's another 4th, making it 1/2. That's another 4th, making it 3/4 of my little segment, and that's another 4th, making it the whole segment, 4 out of 4. Okay, so that means I have to do it at negative pi over 2, and I have to do it at pi over 2, and I have to do it right here, okay, at -2. And then I have to do it right here at 2 because that's my amplitude. And so now this graph, what it's going to look like, I'm going to try to do the best of my ability here. What it's going to look like is something like this-ish. Desmos is going to be so much better at it than me. And same thing here, it's going to be kind of like this. And then this one's kind of odd. It's going to be kind of like that. Okay? So it's weird, I know, because I'm restricting myself to the screen, but that's how you plot it by hand. Why is this important? Well, A, Math Excel is going to ask you more than likely for your asymptotes. So that's why you need to do it by hand. B, they'll more than likely ask you what is that point that's in the middle of the x-intercept. What is the point, the x-intercept that's midway between the asymptotes? That's what it's going to ask you. Okay, so it's going to ask you for those things, and that's why I like doing it really quickly by hand. Now, what does it look like on actual Desmos? Let's go here. I'm going to click on my tangent graph. Come on. This is what it looks like, but I have to change this stuff, right? So my A is definitely not 1/2, so it's 2. And then my B was 1/2. I don't have a C value at all, it's 0. And I don't have a D value at all. So this is what I have. Now watch this. We had a restriction on ours from -2 pi to 2 pi. So that's what I'm going to do. I'm going to actually just copy this. Let's just paste it here. We had from -2 pi to 2 pi. Right? This is what I really had. I mean, that's almost verbatim. Not really. It's almost perfect. It's almost perfect, okay? But it looks pretty good, I think. Okay, it looks pretty good. That's what it would be. If I wanted to add my asymptotes, I could. I have one at -pi and then pi. So I can do x equals pi, and I can do x equals -pi. Okay, those are my asymptotes if I really, really wanted to get intense. And I can change the green. So that's what it really looks like. Okay, that's what we did. It looks pretty good, I think, right? I think it looks pretty good. But yes, you could do it by hand, or you could basically do it by hand on Desmos. I mean, really, you could. Desmos gives you the full graph, but you can restrict it and do everything and plot everything by hand, and it would still work, which is pretty great, I think. So let's go back. Let's erase this, and let's look at my cotangent function. So my cotangent function is very similar to my tangent function. The only difference is it's flipped. Okay, it's literally flipped. So that's what I'm going to put. It's literally flipped. It's the tangent function but flipped. Now remember, these are my asymptotes. I'm going to abbreviate there, asymptotes, and those are where my cotangent function is undefined. If you filled out or printed out the trig table of common angles, you'll see in the trig table of common angles that the cotangent function is actually undefined in a lot of different areas, just like the tangent function. Okay, here are all the characteristics, and it's literally the exact same thing. You have an x-intercept that occurs midway between the pair of asymptotes, and then you have the 1/4 and 3/4 points. So we're going to be using the same thing. It's very similar. We're going to try to graph it by hand, go to Desmos, see if we messed up, and then we're going to go on to the other two reciprocals functions. The other two reciprocal functions. All right. So now let's go and see what we have. Basically, all these steps are the same. Those steps aren't going to change at all. The only thing that's going to change is this, 0 to pi. Okay, instead of negative pi all over 2 to 2 pi, or pi all over 2. Because tangents was negative pi all over 2, and then your little piece, your little mid piece there, your shift, and then pi all over 2. This is 0, your little shift, and then pi. Okay? What's my function? Boom. Remember that this is technically in parentheses, and this is minus 0, and then plus 0 for my d. So this right here is like my bx minus c part. Okay, that's my bx minus c part. So let's try to put it together. I'm going to put 2x, and then I'm going to have pi. Divide each one by 2. Divide each one by 2. That goes poofy. That could become 0. So now I have x and then pi all over 2. So these are where my asymptotes are. 0 and pi over 2. Now, this is really funky. You know why? Because that means, literally, okay? That means that it's going to be very, very skinny. I can even continue this if I wanted to and keep doing, the same points if I wanted to, because it's going to go on forever and ever and ever. I'm just restricting it. So what is this going to look like? Let's do it in red here. X-intercept, so x-intercept, 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 that's occurring midway between the asymptotes. And then the amplitude, we have an amplitude of 3, so it's all the way up here. And now remember, cotangent is flipped, right? So since this is 3, it's flipped. So it doesn't go down to up, it actually goes up to down. So that means I'm going to have a point right here. I'm going to have a point. This is negative 3. I have a point right here, point right here, point right there. And then I have a point right here. And this is a point right here. This is the best we could possibly get it. I mean, it's really hard to find a 1/4 and the 3/4 points when it's so tight. And that's why Desmos is so much better, because we can only kind of briefly look at what it looks like. We can't really program it on pen and paper, but with Desmos, we can actually program it to see what it would look like. Okay, so this is what it would be. It would be like something like this-ish. It's so hard to do on this thing. So easy. It's so much easier to do it when I'm actually in class. Something like that. Something like that. I mean, these just look like just really junky lines. Oh my gosh, I can't even. Okay, so clearly I can't do this. I'm gonna stop right there because that looks like junk. So let's go to Desmos and fix it. Okay. All right. So I'm gonna click out of that. Go to not that. Let's go to cotangent down here. Let's change these things. My amplitude was 3. Okay. My A was 3. My B value was 2. So let's change that to 2. Notice how it's changing. And my C value and D value were that. Okay. I'm going to click out of these. Awesome. So now this is forever. This is as in like it's no restriction. So let's get rid of that and let's put our restriction on it. Boom. That's what it looks like. That's a lot better, I think. Okay, that's definitely a lot better. That's what it looked like. So our restriction was from negative 2 pi to 2 pi. And so I just essentially, yeah, I changed my values and then boom, this is what I have. Okay. It's a lot better than this junk right here. This just looks like a child's drawing. This looks so much better. All right, so that's how you kind of graph it literally by hand on Desmos. Just put the restriction on, and then the rest will do it for you. But the points are still the same. I mean, let's at least give me some credit. I mean, the points are still the same here: pi over 4, 3 pi over 4. At least on here, I had that. But pi over 4, this would be pi over 4. This would be another 1/4 and everything. And then I have asymptotes at pi over 2, which of course you don't see here. But I could put an asymptote at pi over 2. I just, don't. Okay? Awesome. Awesome, awesome. Let's go and erase. Cosecant function. This is a rather funky function. Okay? What it actually looks like is this. I'm going to go over here. This is actually what the cosecant function looks like. Now, are you afraid? Probably. But honestly, a lot of what it is not that hard. I have a lot of added stuff to this. What do I mean by added stuff? If I go over here, there's a couple things you'll see. You'll see the cosecant function, but you also see sine. What? If I take these away, this right here, this itself, this is just the cosecant function. Okay? Really funky indeed. It has a lot of undefined values, just like secant, which we'll see in a little bit. But the reason why I have this, at least in this graph, why I have sine, is because you actually use sine in order to figure out where these points are. Okay, you have to use your reciprocal in order to figure out where those points are. That's awesome, right? So that's why I have that graph there, and I'm going to show you what that means in a little bit. But then I'm probably not going to try to butcher it by graphing it by hand. It seems like that's not helping. So I'll more than likely just jump right to Desmos and try to graph it on Desmos. Okay. But I do have these things, and then this is the asymptotes here. That's the only thing right here. These are the asymptotes that you actually see. So it doesn't look that scary, okay? It shouldn't be that scary. This was the cotangent graph that we saw a little while ago. Very basic, very easy stuff. And then that was the tangent. Really pretty, right? When you put them all together. Huh? No? At least when you put those together, I think they're pretty. So we're going to be focusing on the cosecant graph now. What are the characteristics? Well, first of all, you notice that this is the cosecant, and then you notice right here, there is a sine graph right here. Okay? There is a sine graph right here. So that's sine, right? So you have sine of x. That kind of helps you define your little peaks and your little valleys is what we call them. We use them as little peaks and valleys, okay? The range is really funky. You're not going to really need to know that range. It's very, very, very funky, okay? But you will need to know the vertical asymptotes, integral multiples of pi. So however it changes, basically wherever it crosses the x-axis, that's where your asymptotes are. So where it crosses the x-axis, you see that? That's what we call the integral multiples of pi. When it says integral, it just says x-intercepts. I mean, they're trying to be all fancy. All right. Odd function, yes, we already knew that from a couple of days ago. Here's the domain, and then the period is 2 pi. Why is the period 2 pi? Well, its reciprocal sine has a period of 2 pi, so this is, of course, also going to have a period of 2 pi. So what does that mean? That means this, guys. Your actual period of cosecant, this is what it actually is. This is what the full graph looks like. Just one little parabola right there and an upside down one right there. That's what the full graph looks like. What I have added here is just multiple periods, multiple lengths of pi. Okay, that's the difference. Okay, and then what they have here is also multiple lengths of pi. That's all. Okay, awesome. So the parabolas are going to be at the peaks and valleys of the sine function, and that's what I said before, and that's what I'm going to show you. So first things first, you're going to replace cosecant with sine and then graph that. And that's probably a little bit harder to do, and that's why I'm going to show you the decimals. I'm actually not going to do cosecant and secant for the sake of time. Cosecant and secant I'm not going to do with these graphs, okay? I'm just going to actually leave it to decimals to do the dirty work. But I will show you how to at least maybe graph sine and how to get the amplitude and period and everything, because that's really important. And then we're going to do the vertical asymptotes at each x-intercept and then draw the parabolic curves. Okay, so how do I do this? Well, I'm given this function, 2 times cosecant of 2x. So what does that mean? That means I'm going to replace it with this. F of x equals 2 sine of 2x. Okay, 2 sine of 2x. And then I'm going to actually try to find a couple things here. I need to find my amplitude. I'm going to find my period of that. And then I'm also going to find my phase shift. Okay? So what's my period? What's my amplitude? My amplitude is 2. That's easy. My period is going to be 2 pi all over 2, which of course is just pi. And then I'm going to have my phase shift. So my phase shift is C all over B. My C is actually 0, and my B is 2, so this becomes 0. Sweet. Now, how am I supposed to graph this? Well, it's not shifting anywhere, so that means your starting point is right here. Your amplitude is all the way up to 2, okay? Yeah, your amplitude is all the way up to 2, so if this is, let's just say this is 2, that means it's going to go all the way up here and then down and so forth. But my period is pi, so that means I have a period right here, okay? It only goes from here to here. So what this would look like is something like this. That's what my sine graph looks like, not my cosecant. That's what my sine graph looks like. And that's my other asymptote. Notice how where it crosses the x-axis is where my asymptotes are. So then if I want to find my cosecant would be in blue here. It would be, I need to do my asymptote right there too. I forgot an asymptote. Also crosses here. And so what is my cosecant graph is now really straightforward, right there and then right here. So that was actually really easy, and so I guess I'm going back on my word. I'll still show you how to do it on decimals, but that one was really easy, okay? Very, very simple. Now, could I expand it to the left? Yes. Could I expand it more here? Yes. But this is the very basic graph from 0 to pi. Basically, the length of its period, that's what I just did. Okay, so what's in blue here is your actual graph. If that's confusing, I'm sorry, erase all the red, okay? And then you just get your blue graph and that's it. So what does this look like in decimals? Let's find out. Okay, so I don't want cotangent anymore. I want cosecant, okay? Let's do this, copy, do that. And let's actually reduce this down to just 0. And then pi, yeah. Boom. That's not my actual answer. Okay, so my A we said was 2, and then my B we said was 2. Yeah, so it was very close. It was very close. That's what it looks like. Okay, so if we go back, that's what I graphed, and then right here. Now, if we did graph that, if we put sine right next to it, Watch this. If I copy and then put sign right next to it and then paste, whoops, that was the wrong copy. I don't want to do that. Copy, and then we paste it over here. Notice that's my sine graph, what I just did. Okay, and this is my cosecant graph. So they're very, very related, and they touch right at that point, those points there. So Desmos is awesome because they give us these points, and we can kind of like, yay. And that's exactly what we did. And so our asymptotes are right here at the 0, asymptote is right here at pi over 2, asymptote right here at pi, just like what we drew here. Okay? Not too bad. I'm not gonna lie. Not too bad at all. Okay. So we did everything. We got everything. Awesome. So now let's erase. Let's go to our last graph. Secant. Okay. Very similar. I mean, by similar, I mean like literally the exact same thing. Besides, it's going to be, secant. And instead of sine, you're going to be using cosine. So this is what the graph actually looks like. This is your cosine graph right here where my mouse is. And this, I can use my laser pointer. Isn't that great? This is where your cosine graph is right here. And this right here is your actual secant graph. Okay? This is your actual secant graph. And this is your cosine graph. Sweet. These are your asymptotes. They occur odd multiples of pi over 2. That's what it says right here. Let me move this up right there. It occurs every odd multiples of pi over 2. And then it is an even function because, of course, it's the reciprocal of cosine, and cosine is an even function, and so forth. All right? Awesome. Let's go to town. Let's hit it. Exact same steps. This is my graph. I'm going to try my very best to graph this. First things first, though, I need not secant. This is going to be y equals negative 3 cosine. And then this is going to be 1/2 x. Okay, so what does that mean? Well, first of all, my amplitude is 3. Okay, absolute value of negative 3 is 3. Secondly, I have, whatchamacallit, my period, which is 2 pi all over b, so 2 pi, and then all over b, which is 1/2. So multiply by the reciprocal times 2, this is 4 pi. So that's a lengthy period. That means the whole thing is going to expand like straight up 2 revolutions. So this is really a nasty one to graph. Maybe we won't graph it. And then 3 is going to be for my phase shift. Now my phase shift is c all over b. But in this case, there's really nothing here because there's no c value. So that means just 0. All right. Now, draw the vertical asymptotes at each x-intercept. This is going to be rather tricky. Tricky indeed. And that's probably why I'm not going to graph it here. I'm just going to go straight to Desmos. The reason why this one is tricky is because the period is so freaking large. It's so big, right? And so it's harder to kind of see where the x-intercepts will be if you don't have the actual graph. By actual graph, I mean the original graph. Now, if we go back, if we went back, we can see that this is the original graph. And so your x-intercepts occur right here, but they're not going to occur at negative pi over 2 anymore, okay, because the period is going to be shifted so large. And that's the hard part, you know what I mean? And so that's why I think this one is probably best just to go to Desmos. Let's go to Desmos and see what happens here. Let's turn this off. Let's go here. All right, this is your secant graph. What was our A? Our A was negative 3, so I'm going to type that in. My B value was 1/2. So 1 divided by 2. And then I didn't have any C value. So this is what it is. That's not bad. It's not bad at all, I guess. But let's do our restrictions. So what would it look like on our graph? So our restrictions here was negative 2 pi and then 2 pi. So let's do those restrictions because that's where it kind of blocked off. If I were to put it on this screen, what would it look like? Negative 2 pi to 2 pi. Let's find out. Let's go to here. Let's do our restrictions. So negative 2 pi. And then let's just add that 2 here. Okay, so this is what it will look like. It's rather fat. It's rather fat, and then That's okay. So these are kind of cut off, as you can tell. So if we were to graph it right here, it would be cut off. And so this is cut off, and that right here is not that your full length of a nice peak, I guess. It's a nice peak. Not bad at all. That's what it'll look like. So you can graph that if you want. You can actually write it down in your notes. That's amazing. Let's go back, erase, and then let's go through our summary. So I hope you understood our graphing week of unit circles, and then 5.5 for graphing sine and trig, or sine and cosine, and then just the other trig functions, cotangent, cosecant, and so forth. What do we learn today? Basically the same thing that we learned with 5.5, but now with tangent and reciprocal. So we learned how to understand the graph and the variations of tangent and reciprocal trig functions. We also use vertical shifts of tangent and the reciprocal functions. We did technically model the periodic behavior because it does go back and forth. So after a couple asymptotes, then you have another one, then you have another one, and another one, and another one, and so forth. You'd have to restrict off those sections in Desmos if you want to slice off that periodic behavior there. Awesome. So homework quiz tomorrow. Again, 2 extra credit points on the homework quiz for just 100% on the homework. If you have any questions or any concerns, just please email me. But until then, guys, I'm excited to just continue teaching you trig. So keep watching the videos, and tomorrow we'll have a Desmos activity. So this is C Squared Mathematics. I'm Mr. Carlson. See you guys later.